Alright, so just like everything before, we have a test to see if the correlation we observe in a data set, if it's significant or not. Okay, so we have a brief hypothesis test to see, is the correlation that we observed significant, or could we just get this correlation value just from random chance? Okay, so test for significance. Okay, and your null hypothesis is that there really is no relationship between x and y. Okay. X and y. And any correlation that we observe is just a result of random chance. Right? If I look at people's IQ scores and their shoe sizes, there's no real relationship in real life. But maybe by random chance, if I picked 4 people, it could be possible that by random chance, the people with big shoes had lower IQs and the people with small shoes had high IQs, and I might be misled to believe that there is a negative relationship between shoe size and IQ. Okay? So that could happen just by random chance. So, and the alternative is that there is a relationship. Okay. Okay, so symbolically, so R is the symbol that we use for the observed correlation in a sample. What do you think the letter we will use would be for the correlation in a population? It's the Greek letter that corresponds to R, which is rho. And rho, oddly enough, looks like a P. But it's rho is equal to 0, and the alternative is rho either does not equal 0, or you could also have rho is greater than 0 or less than 0, depending on what you want to say for your alternative. That's rho is the correlation that exists in the population. I feel like we've done enough hypothesis testing where I don't have to go into super great detail about what's happening here. And we won't talk about how this thing came about, but you just need to have written down somewhere that the test statistic that you use to test for significance is equal to R times the square root of n minus 2 over 1 minus R squared. And this follows, oddly enough, it follows a t-distribution. Follows a t-distribution with n minus 2 degrees of freedom. So that seems like it's totally random. The n minus 2 comes from the fact that 2 points define a line. 2 points define a line, right? So if I only have 2 data points, and you calculate correlation, it's always going to be 1, right? If you only have 2 data points. So the question is, if I throw in a third data point, is this could that happen just by random chance or what, right? So this follows a t-distribution with n minus 2 degrees of freedom. So you just plug in your numbers, you get this test statistic, and you look it up in the t-table with n minus 2 degrees of freedom. You get a p-value, and you decide whether or not to reject the null hypothesis. Okay, and if your alternative is non-directional, you take that and double the tail area for your p-value, and if it was directional, you just leave as is. Is that all right? Okay, I feel like we've done enough t-tests or something similar. So it's just now you have this new formula here to get the test statistic. Okay. And so maybe so just a few just a cautionary notes, I guess. Okay, and maybe you will always hear this, but correlation does not equal causation. Right? So you might see there's definitely a relationship between 2 variables, and this applies whether it's 2 numeric variables and we're looking at correlation, or maybe even with a t-test, right? In a t-test, you've got 2 groups, and you see there's a significant difference between the 2 groups. Okay. But just because you do see a relationship exists, it does not mean that one causes the other. Okay. A relationship, just because a relationship exists, about this briefly already, but for example, if we looked at all the countries across the world, so there's about 200 of them, and we looked at basically cell phone adoption rates, okay, so that's a numeric variable, and so in the United States it's like, I don't know, 80% or something of people have cell phones or something like that. And when you go to other countries, and maybe only 20% of people have cell phones. And so that's a numeric variable. And we can look at life expectancy. Okay, so we can look at cell phone adoption rate versus life expectancy. What you will see is that countries where more people use cell phones tend to have longer life expectancy. Okay? And you'll see positive R. And say there's evidence. So when you do the test, it will be significant, and you can say there is evidence of positive correlation between cell phone adoption rate and the country's life expectancy. So does that mean if we want to increase a country's life expectancy, we just got to get more people to use cell phones? No, of course not. Okay, we know that would be a silly idea. And what's really going on is there's an underlying variable in the country's country that's maybe economic or economic stability or growth, power and infrastructure, where if there's more infrastructure, you will have more people using cell phones, and greater infrastructure also means probably better health care and better things like that increase a country's life expectancy. So there's something else going on that's causing both of these things. Okay? So in this silly example, it's easy to see that correlation does not equal causation. But many times you will read articles where people make the wrong conclusions here. Okay, so a lot of times in newspapers, a lot of organizations are very guilty. They'll say, "Oh, you know what? After we implemented some increasing the number of police on the street somehow has increased or decreased something else." Okay, so yeah.
Is there a statistical way to determine if X is actually causing Y, or is it just using intuition?
You have to do an experiment. Okay. So the true answer is you must do an experiment where you do random assignment, okay, and then you can do it. But obviously, with something like experiments aren't always possible, okay, and the best data we have is observational studies, okay. And so when you do an observational study, it's hard to determine causation, okay. And you have researchers who dedicate their life to trying to determine causation based on observational studies, because this is kind of like the magic bullet in statistics. Okay, if somebody can figure out a way to get causation from an observational study, this would be a huge breakthrough. Okay, and so you have a lot of researchers working on this, and they have some methods that are kind of good, but we're not really there yet. Okay, and, but yeah, if you want to be able to determine causation, you've got to do an experiment. But experiments aren't always possible, and so we're always trying to figure out what can be done. What can be done. So at this level of a stats class, we're just going to say observational studies. You can't determine causation. But there's a topic, I forgot the name of it. So that's like the area that people are working on to see if causation is related to. It can be found from an observational study. Okay, so once you figure out correlation, we can work on finding the regression line. Okay. So now we are going to talk about linear regression. So with linear regression, what we are trying to do is we are trying to fit a straight line, that our best fitting straight line for the data. Okay. So here we are trying to basically fit a straight line to the data. So the big so regression, this originally came up back in the days of the early 1900s, late 1800s, Francis Galton, they were trying to find a relationship between measurements of people's body parts and whether or not this person was going to be a criminal. Okay, because there was an idea that criminals had something in their genetic structure that, or in their genetics that made them behave a certain way, and maybe this could be measured somehow through measurements. Okay, and that was actually that was the beginning of looking at fingerprints, and they found out that fingerprints are a way to ID people, but it wasn't because they were trying to figure out a way to ID people. This was like a happy accident from taking all these measurements on people. But okay, but anyway, as people were looking at all of this data, an interesting thing was, can we predict the height of a man based on the height of this person's father? Okay, so can we predict the height of a man based on his father's height? So, what do you think the answer is?
Not accurately.
Not accurately, but sure. Okay, I mean, we can always throw out a prediction. Okay, and in general, is there a trend between a man's height and his father's height? Yeah, in general, men who are above average in height tend to also have fathers who are above average in height, and in general, men who are below average in height tend to have fathers who are below average in height. But of course, this is not the only thing that determines a man's height. Okay, the father's height is not the only thing that determines a man's height. Okay. So anyway, when we do regression, we have to determine the x variable and the y variable. Okay, so the x variable is the variable that we use to make the prediction. So based on our x variable, we make a prediction about the y variable. Okay? We use to make the prediction. So y is the variable that we are predicting. So in this case, what's my x and what's my y variable?
The x is the father.
Yeah, x is the height of the father. And y is the height of the son. And so we look at a bunch of data here, okay? And let's say the average height of the father was 69.5 inches. Okay, and let's say the average height of the son was 70 inches. And when we looked at the standard deviation of all the father's heights, let's say the standard deviation of all of these heights was 3 inches. And let's say the standard deviation of all the son's heights was 3 inches. So one notion that people had at the beginning was, oh, okay, if the standard deviation of the father's height is 3 inches and the standard deviation of the son's heights is also 3 inches, we could just take a ratio between the y and the x variable and kind of create a slope, right? Because we talk about, the slope is often thought of as the change in x over the change in y over the change in x, or the rise over the run, okay? So from algebra, the rise over run, or basically change in y over change in x. Okay. So one notion was using the standard deviation straight up, okay? Is that the slope can be the standard deviation of y divided by the standard deviation of x. So we have 3.0 over 3.0, and I get a slope of 1. So what this slope of 1 means is that if the father is 1 inch above the mean, I predict the son to be 1 inch above the mean. And if the father is 2 inches below the mean, I would make a prediction that the son is 2 inches below the mean. Okay, that's what the slope of 1 means. Okay, I take how much is the father above the mean, I multiply it by the slope, and that's how much I predict the son is going to be above or below the mean. Okay, does that make sense? So does that seem like an appropriate slope? Okay, it seemed appropriate at first. Okay, and they said, oh, okay, that kind of makes sense. But then when they looked at the data, it was a terrible fit. It was a terrible fit. Okay? And the reason for this is that the son's height is not entirely determined by the father's height. Okay? And what we saw is that what the data showed was that maybe there was a father who was, let's say, 6 inches above the mean. Okay? So if the mean was 70 inches, 69 and a half, okay. Maybe there was a father who was 6 inches taller than the mean, so a good deal taller than the mean. What often happened was that the son was rarely equally that far above the mean. Okay, if the father was 6 inches above the mean, the son was rarely 6 inches above the mean. Usually, the son would be taller than average, but not 6 inches above the mean. So if the father was like 6 inches above the mean, maybe the son would be 5 inches above the mean. Okay, and the same happened when we went in the opposite direction. If the father was, let's say, 6 inches below the mean, rarely was the son also 6 inches below the mean. The son might be maybe 4 inches below the mean or 5 inches below the mean. So, and we gathered lots of data, and so, very rarely, the father would be 6 inches above the mean and the son would be 7 inches above the mean or something. So that happened, but it was very rare. But overall, what the data showed was that if the x variable was, a great distance from the mean, the y variable would generally be also above the mean, but not as far. Okay. And so this 1-to-1 ratio of how much the y changed versus how much the x changed was too extreme for pretty much almost all the scenarios that they looked at. And so they found that a much better slope was one that was tempered by the correlation coefficient. Okay, so the best slope was actually looking at the ratio, the standard deviation of y over the standard deviation of x, but multiplied by the correlation. So maybe if correlation was 0.7, okay, maybe it would be 7 times 3.0 over 3.0, and we get a slope of 0.7. So what this would say was that if the father was 6 inches above the mean, we predicted the son to be 6 times 0.7, or 4.2 inches above the mean. And this illustrated, and this is where the term regression came from, regression. Because when we think of regression, we usually think of taking a few steps back, right? Somebody regresses. And this was the idea that whatever we were predicting tended to regress or go back towards the mean. Meaning, if a father was 6 inches above the mean, the son was rarely 6 inches, also 6 inches above the mean. The son would be above the mean, but not as much, meaning the height of the son regressed towards the mean, or regressed towards the average. So that's where that term regression came from. Okay, so with linear regression, we're trying to fit a straight line to the data. And we had to determine the equation of a line. If you think from algebra, the equation of a line is y equals mx plus b, where m is the slope and b is the intercept. Okay? In statistics, we change up the letters on you. Okay? This time to show that we are not actually looking at values of y. We are just making predictions. We put a hat over the y to signify that this is the way we are predicting y. Okay. And the intercept we call b0, and the slope is b1. Okay. So the intercept is b0, the slope is b1, and that's just a notational thing. There we go. We showed you the equation for the slope, b1. The slope is equal to r times the standard deviation of y divided by the standard deviation of x. And the intercept is equal to y bar minus b1 x bar. Do you guys remember point slope form? No, okay, that's all right. Basically, this is point slope form. This ensures, by choosing this to be your intercept, by setting the intercept as this, okay, the line will run through the point x bar, y bar, okay? So the center of all of your data, meaning the mean of x and the mean of y, the best fit line is going to run through that middle point by using that as your intercept. Okay, why is this our best fit line? Why is this our best fit line? The best fit line is determined by something known as the sum of squares residuals, okay? Okay, so a residual is the difference between what we predicted and what the actual point was. Okay, so a residual is equal to the difference between the actual y value minus what we predicted for y. Okay, or in symbolically, a residual is e kind of like an error, and it's y minus y hat, the prediction for y. Okay, so let me just kind of illustrate. Let's say this was the data points that I have. Okay, this is my actual point, alright? For this particular x value, okay, so if my x is right here, what is the value that I predict y to be equal according to this line? According to the line, I make my prediction to be right here. This is where the y hat is for that particular x. But the actual value is right here. So this distance from here to here, this distance is the residual. Okay, so the vertical distance from the dot to the line is the residual. So I predict the point to be right here. According to, for a point with this x value, okay, I'm predicting the point to be right here. But in actuality, the point is down here. So this distance right here is a residual. Okay. So a positive residual means what? The actual point is larger than the prediction. Okay. And a negative residual means just the opposite. That the actual point was smaller than the prediction. Okay. So let me draw try to draw two identical sets of points. Okay, close enough. Alright, so let's say these are my two sets of points. And so how do we know if one line is better than another, okay? So somebody might say, oh, the best fit line is this. And somebody might say, no, the best fit line is this, okay? How do we decide which line is better? Okay? Well, what we're going to do is we're going to take a look at the residuals, okay? So according to the residuals, and then, so let me draw the residuals. Okay, so here's the residual, and there's the residual, and there's a residual, and there's a residual, and there's a residual. And here are the residuals over here. So those are my residuals. I'm going to, we're going to look at the sum of the squares residuals. Okay, so I'm going to take these residuals and I'm going to square them. So whatever this distance is, I'm going to make a square. And I make a square for that one, and I make a square for this one, and this one, and okay, and I do the same with these guys. Okay. And I sum up the total size of all of these squares. Okay. I add up, I sum the squares of the residuals. Okay. Can you guys see that these are residual squared? Yeah? Okay. So it's the residual, and I'm literally drawing a square using the length of the residual as the length of the side of the square. Okay, so this is the sum of squares residual for this line, and this is the sum of squares residuals for this line. Okay. And whichever line has the smaller sum of squares is the one that we pick. Okay. Line with smaller sum of squares, sum of squares residuals, is the better fitting line. Well, how do we find the best fit line? Well, if you've taken calculus, you can minimize an equation by taking the derivative, setting the derivative equal to 0, and searching for these critical values, okay? Well, the smart people did that, and what they came down to was that the best fitting line is the one that has this slope and this intercept, okay? So we get to benefit from other people's hard work and just know that this is going to be the best fitting line, and not have to worry about calculating the sum of squares for every single line or possible line. Okay. So let me erase this, and so there's one last thing I want to talk about, and that is r squared. Okay. Well, you know what? Let me actually talk a little bit more about the slope and the intercept, the interpretation of these things. Okay, so let's say we looked at this father-son type data. What did I say? I said the average height of the fathers was 69.5, and the average height of the sons was 70, and the standard deviation of x was 3, and the standard deviation of y was 3. And let's say the correlation was 0.7. Okay, and it's probably actually not even that big. So let's figure out our best fit line. Well, B1 deviation of y, which is 3, divided by the standard deviation of x, which is 3, I get a slope of 0.7. What is my intercept? My intercept is going to be 69.5 minus my slope, which I just calculated to be 0.7, multiplied by 70. Okay. So I get so my slope is 20.5. So putting it all together, I get y hat is equal to 20.5 plus 0.7 x. So my slope is equal to 0.7. What does this mean? The interpretation of the slope is this. For each additional unit of x, we expect or predict y to increase by the amount of the slope. So in this case, for every additional inch we have in the father's height, we predict the son's height to go up by 0.7 inches. Is predict, because a son's height is not entirely determined by the father's height. So we're predicting the son's height to go up by 0.7 inches, but not always. On the other hand, the intercept is 20.5. And the interpretation of the intercept is this. If x were equal to 0, we predict y to be the value of the intercept. Now, this will not always have a meaningful interpretation. Here we are saying if the father were 0 inches tall, we predict the son to be 20.5 inches, okay? But that makes no sense because no human could be 0 inches tall, okay? Because that would just be not a person, okay? So that's what that means, okay? But other times it might make sense to have a 0 for the x value. I wanted to talk about R squared, but before I do that, more about maybe some warnings with regression, okay? Okay, because when you do regression, it seems like, oh, cool, I can do all sorts of stuff. One warning is, do not use the regression line to make predictions outside of the range where you've collected data. So a silly example could be maybe you are measuring a child's height versus their age, okay? And so the x variable is the age, and the y variable is the height. And so, years, from age 5 to age 10, it seems every year the child grows a couple inches, okay? And so you see a steady increase, from age 5 to 10 or whatever. You see this. So you can fit this regression line, and you might be tempted to then say, oh, Timmy grows 2.5 inches every single, or 2 inches every single year, okay? And so by the time he's age 40, he's going to be, whatever, 20 feet tall, okay? That'd be silly, right? Because, what happens is that at a certain point, the height levels out, okay? But if you only saw this part, okay, so if you were an alien, okay, an alien from another planet, and you captured a human child, and you saw every year this child is getting taller and taller and taller, you might be worried. Oh no, this child, in 50 years, he will be 20 feet tall and will overthrow our government or something, that'd be silly. But when you look only at the data, you have no idea what it looks like outside of the range where you've collected data, okay? So the regression line, and it seems silly, talking about predictions, but it's best for, oh, okay, how tall, can we make a prediction for how tall Timmy was between his 6th birthday and 7th birthday? Sure, we can do that. But can we see how tall he's going to be in 20 years? No, we don't know that, okay? Because, a lot of times, maybe in one region, the part is linear, but we have no idea if it goes like this, or if it goes like this, or if it goes like this, or if it goes like this, okay? So inside this part, that's all we see. And in the opposite direction, the same types of things can happen, okay? So we have no idea what happens outside of the range where we collected data. But you see people abusing this all the time, right? They say, oh, between years 1990 and 2010, this has happened, so we are on track to have this major catastrophic event by the year 2030 or something, right? They always say this is going to happen 20 years into the future, and the truth is nobody knows what's going to happen 20 years into the future, okay? So we can see all sorts of stuff, and it's good, linear regression has its use, but it can definitely be abused by people with certain agendas or whatever they might be. Okay. What else? Oh, be very if you have outliers in your data. saying just throw away any outliers that you have, okay? Only throw away data if you can justify removing it. Okay, so for example, let's say, we were talking about, someone's shoe size and their IQ. And probably if you gathered a bunch of data, it would look like this, okay? And you'd see no real relationship. But there was, so Bozo the Clown, I don't know if you remember, Bozo the Clown had unreasonably large feet, okay? And he was actually also very, very smart, okay? So he would probably show up something like this, all right, in terms of the shoe scale here, okay? So he's an outlier, and because of this, the regression line will probably look something like this, okay? And you might come to the incorrect conclusion that that people with larger feet are smarter or something like that, or have higher IQs, okay? So this outlier can mess up, can throw off the analysis. After you fit the line, okay, there should be absolutely no pattern in the residuals, okay? So after you fit the regression line, there should be no distinguishing, no pattern in the residuals, okay? And then this is what I mean by that. So here you've got some data here. Okay. What we do is after we fit this line, we should take a look at the residuals here, okay? Which is basically like almost as if we've taken the line and we've flattened it out, and we are looking at the values of the residuals. So we would see this type of thing. In here, we should see no pattern. It should look like the residuals are just randomly scattered, okay? And the reason for this is, let's say we had a situation where after we fit our data, we see a pattern like this in the residuals, okay? When we have our best fit line should be our absolute best should reflect our absolute best ability to make predictions, okay? And when there's no pattern in the residuals, that tells us that, yeah, I couldn't make any better prediction, and when my predictions were wrong, which is what the residuals are, I had no idea if my predictions would be too big or too small, okay? So I have no idea if the residuals are going to be positive or negative. When you've got a pattern like this, here we can see, oh, you know what, down in here we've got positive residuals, over here we've got negative residuals, and over here I've got positive residuals again, okay? What that means is that somebody could look at this pattern and further improve my predictions. They could say, oh, you know what, I've got, if I'm in this region, my predictions are probably too low, and if I'm in this region, my predictions are probably too high, and they can further tweak our predictions, okay? And that would be a reflection that your best fit line is really not the best prediction that you can do. Okay, so when you fit the regression line, there should be no pattern in the residuals, meaning that you can't really improve your predictions beyond what they are.
Which one of those is a pattern? Both of them?
So this one, we kind of see a pattern like this, and over here there's no pattern here.
Well, the top ones are taller than the bottom ones.
Oh.
So does that mean you should move the line up?
Probably, yeah, if something like that happened. Okay, the residuals, one of the rules in linear regression is that the residuals, when you add the positives and the negatives, it zeroes out. Okay, this is just a bad graph.
Okay. But how would you make a line that would fix that? There is no line that would fix that, right?
For the bottom one?
Yeah.
Yeah. This would be an indicator that linear regression
Oh.
is not a good thing. Okay, there's more statistical regression tools. We're only learning the most basic one, linear regression. But there's more tools out there, and you just have to say, oh, I don't know how to do this, but what I have is not good. Okay, sorry. Last bit, we gotta cover R squared. So when you take the R and you square it, you get R squared, okay? That seems obvious, but in our case, it grows up and it becomes capital R squared, okay? And this thing is, and these two are equivalent for linear regression, okay? For linear regression, these two things are equivalent. For complicated regression, they're not. But this is also known as the coefficient of determination. This fancy name. Okay. So for our regression, father-son regression data, our R was 0.7. So my R squared would be 0.7 squared equal to 0.49. So 0.49 is my coefficient of determination. What this is the amount of variation in Y that can be explained by the regression model. Okay. And because our regression model is linear, it's just that can be explained by X. Okay. The amount of variation in Y that can be explained by X. So what does this mean? It means, so we're going to say 49% of the variation in Y can be explained by X. So in our case, 49% of the variation can be explained by X. Alright, what was Y again for our father-son height data? Y was the height of the son, okay? And X was the height of the father. So in this case, what we're saying is that, you know what? The things that determine how tall a man is, okay, how tall a son is, there's a whole bunch of things, okay? Height of the father, height of the mother, what he ate, you know, whether or not he drank coffee as a kid, I don't know, right? That's what they say. So there's all sorts of things that go into determining how tall a man ends up being, okay? And what this is saying is that in all that variation of, you know, you look at a bunch of different people and they're all different heights, well, 49% of that variation can be explained by the fact that his father was this much taller than average or this much shorter than average, okay? So if you think back to ANOVA from last week, we basically split up the total sum of squares into parts that were explained by the different categories and parts that were just people are different, right? So here what we've got is 49% can be explained by the fact that the X values are different for these people. And the other 51% it cannot be explained by our model. It's just the fact that people are different. There's other things going on into determining why someone might be taller or shorter than someone else, okay? So 49% of the variation in a man's height can be explained basically by father's height. That's r squared on the coefficient of determination. Okay, that's all I've got. You guys have some homework problems to go over chapter 12, and we'll see you guys next week for kind of just a recap and review of the whole quarter.